Hi, this is the fourth lecture on the Advanced Geostatistics course about spatial uncertainty assessment. Okay, in this lecture, we are going to see the main geostatistical simulation methods for continuous variable. The methods that we are going to see are based on the sequential approach, as we have seen in previous lecture. And there are basically three methods. The sequential indicator simulation, just this one, sequential indicator simulation, which is based on the indicator formalism to estimate the local conditional distribution functions. The second method is sequential Gaussian simulation based on multi-Gaussian kriging to estimate those local CDFs, and direct sequential simulation it uses the original variables to estimate the local CDF, as you are going to see. So let's start by the sequential indicator simulation. So basically, all those methods follow the same outline. First, define a random path, which visits each one of the nodes of a grid, a regular grid. For example, let's take the example. We choose this one, x8. We have 7 samples, so sample values, sorry. Yeah, and we are going to estimate the local CDF at x8 location. So the estimation of conditional distribution functions at a grid node x8 is conditioned to experimental samples by using the indicator kriging approach, as you've seen in a previous lecture. So for each class, we define an indicator and we krig this indicator, obtaining a conditional distribution function for the cumulative probability for this class here. In short, the values, my original variables, values of original variable, for example, porosity, soil content, and so on, are transformed in indicator for each class. So I must have k indicators. To calculate the conditional distribution function is equivalent to estimate by krigging each one of the indicator variables, like this here, this expression. And just a note, just to remind you that to solve these k IK systems, we have one system for each class. One needs the k covariance models or variogram models. Once the k values are estimated, they are eventually corrected by order relations. Let me remind you that sometimes there are order relation violations. When the class limits, for example, z1 and z2, z2 is greater than z1. But as we estimate the indicators separately, with different variogram models, we do not guarantee that the estimated cumulative probability of Z2 is greater than the equivalent cumulative probability of Z1. But in this case, we usually do a simple order correction. So, after we reconstruct the local CDF at X8, we perform a Monte Carlo simulation by, for example, inverse method, which means, to remind you, we generate a random number p and we back transform to obtain the original variable zx8 at this location. Okay. So the simulated value is added to the set of experimental values. And we proceed by randomly choose another location to be simulated, x9 for example, and we loop until all grid nodes are simulated. Okay. Note, just one important note. Given the need to estimate variograms and to model the variograms for each result, each class, and check the order relation violations. For example, after kriging, this sequential indicator simulation is not a very common method to simulate continuous variable because it's a cumbersome method, in fact. Unless there is a particular situation where SIS, sequential indicator simulation, is highly recommended, when it's a clear evidence here of different spatial continuity patterns of extreme classes that can only be revealed by indicator variograms of those classes. In this case, the SIS can be recommended. Now let's see the second method, sequential Gaussian simulation. So this method is based on multi-Gaussian kriging approach to estimate the local CDFs. As we have seen in previous lectures, multi-Gaussian kriging assumes that our variable is multi-Gaussian distributed. So so the original variable z of x, which is not Gaussian, must be at very beginning must be transformed in the standard Gaussian variable through a normal score transformation. It's a simple one, which means that for any original variable z of x, we look for the equivalent Gaussian value y of x with the same cumulative probability. So after we transform all our experimental values in Gaussian, we must assume, this is extremely important, we must assume this variable is multi-Gaussian distributed. This cannot be validated. This is an assumption, okay, as we've seen. So let's summarize the main steps of sequential Gaussian simulation. First, define a random path over a regular grid of nodes to be simulated. It's a classical procedure in all sequential algorithms. So estimation in the first node, the local parameters, simple kriging mean and variance, using the n experimental samples here, okay. The estimation of local mean and variance are based on Gaussian variograms, which is just one, and based on those two parameters, mean and local mean and variance, the cumulative distribution, Gaussian cumulative distribution, is entirely defined with just those two parameters here. Okay, as we know. This cumulative distribution is defined. Now the last step is to draw a value to generate a simulated Gaussian value by draw a value from uniform distribution and using the inverse method to obtain this simulated Gaussian value at x8 location. So after that, the simulated value is added to the data set, which becomes n+1 values, and we loop until all nodes are simulated. Now, it's important. The last step consists in the back transformation of simulated values, all simulated values in original variable. Okay. Now, let's see the third method that I would like to present to you today, which is direct sequential simulation. So the previous methods, as you have seen, imply the transformation of original variable. Sequential indicator simulation transforms the original variable into indicator, and sequential Gaussian simulation transforms the original variable into Gaussian values. The direct sequential simulation does not, it's important, perform any transformation of the original variables, which implies several advantages over the two previous methods. So there's one principle that gave rise to this method, direct sequential simulation. If we follow the sequential random path, no matter the local CDFs we use, if they are centered on simple Kriging estimator, then the variogram are reproduced at the end, which is one goal of the simulation method, but unfortunately not the histograms or the global probability distribution, which is the second main goal of stochastic simulation methods. Now, the idea of this direct sequential simulation is this one simple idea that uses the local mean estimator and variance with original variable, not to define the local distributions that you as you have done in the previous methodologies, but to resample the global distribution. Assume this is the global distribution here. Okay, so after we estimate the local mean and variance, you use those two parameters to define an interval of my global distribution to resample a simulated value. Okay, this interval is centered in the mean, and the range of the interval is proportional to the variance. Okay. So let's see the main steps of direct sequential simulation after we define random paths over regular grid of nodes to be simulated. We estimate local mean and variance, identified respectively with the simple Kriging estimator and simple Kriging variance, conditioned to the experimental samples. Surrounding samples zxi and to the previous simulated values zs of xi. So we define, after we estimate those two parameters, local mean and variance, we define the interval to be sampled from the global distribution. And this interval here is centered at the mean, estimated mean, local mean, and the range is proportional to the variance. If this, in this case, as you can see or you can imagine, the local mean is high value, was a high value, or could be a low value, and so on. And the range of the interval is more spread or less spread, depending on the variance. So after we extract the values of this interval, we create a local cumulative distribution function. Okay, and we simulate a value z simulate a value from that distribution, local distribution. Okay, classical inverse method that you have seen previously, and we'll repeat those steps until all nodes are every node is simulated. These are examples of simulated realization, no matter is SGS, sequential Gaussian simulation, direct sequential simulation. It represents is a 2D representation, for example, soil sample data of our samples, and those are realizations of simulated realizations of this variable here, the soil contaminant, porosity, whatever. Now let's see how to check. This is important check. After we run a simulation, we have to check if it makes sense or not. This is the first check. Any simulated realizations must honor the data points. It means that at sample locations, the simulated value is equal to the experimental data. You have to check here if they are reproduced. Otherwise, there's some problems in the normal geographic coordinate system. Okay. The second check is the reproducing of the statistics of data points. Okay. We must check if, for example, it represents the histogram of our data, experimental data, and we must see if the simulated realization, 1 or 2 or 3 realization, reproduce the histograms or the mean or variance. Okay, it does not mean that it is exactly the same histogram, but is similar histogram, similar mean and variance, depending on the realization. There's some fluctuation of the ensemble of realization. The third check is the reproducing of variograms, spatial continuities. As you have seen, this is one main goal, to reproduce the variograms. In this image here, you can see the simulated realization. We compute the variograms, and you can see this north-south, east-west, where the green line is the variogram. This green line here, set of points, sorry, is the variogram of simulated values, and in a blue line we have the variogram model we imposed to the simulation. In these cases, as you can see for this another realization, in these cases you can consider quite satisfactory match between the obtained variograms of our simulations and the imposed models. Now, let's see how to extract the uncertainty from a set of simulated models. Remember that this is one of the main purposes, the main goals of those simulation models. Suppose here we have represented simulated 3D models. This is 3D models of porosity. This is in depth. Okay, this dimension is the depth of porosity. We have a set of n simulated models, and from each set of simulated, you can compute, for example, the mean in each pixel. You compute the mean of each pixel, and you obtain this image, very smooth image, as you can see. Let me remind you, this mean is equivalent to the kriging, the most probable models. But let me tell you that in some situations of high skew distributions, the median is more robust in the sense of this less sensitive to the extreme values. Okay, but we also have we have the measures of uncertainty. Here we can compute the first quartile. In each pixel, we have for example, another realization can compute the first quartile for each pixel, and you obtain this one. Okay, and the third quartile. Remember that as it is a porosity model, the first and third quartile corresponds, for example, corresponds to the most optimistic and conservative scenarios about the potential local sand reservoirs, for example. But the interquartile range, Q3 minus Q1, is a robust measure of local uncertainty and risk. Okay? We can compute minimum, maximum, but also we can compute the variance, which is another measure of uncertainty. And you can see the local areas where the local areas of high uncertainty, local uncertainty, more variability of the values. As you can see, the areas of high values, the high values of porosity corresponds to also the high uncertainty in this case. This is another example of 2D simulated models of soil contaminant. We have here the generated realizations and the mean, first quartile, third quartile, and the variance here. Now, let's see a different chapter. When you simulate the simulation with secondary data or auxiliary data. In those situations, we do have a secondary variable, another variable that can enrich the simulation models of what we call primary variable. Okay, and you use those auxiliary variables to enrich the final model of our target variable. So we are going to see basically two models. There's a lot of more, but this is the most common models, which is simulation with local means and joint simulation. So simulation with local means. Well, this is refers to those situations that we have a model of a variable v1, for example, porosity, which can be considered a good trend model of the the other variable v2, permeability. For example, this is the B plot. The B plot porosity and permeability, and you can see a good relationship. And suppose this is the mean value of porosity model obtained by Kriging or obtained by the mean of simulated of porosity realization. But you can consider, it's an assumption, we can consider a good local trend of the permeability, and we are going to use the mean model of porosity as a trend to simulate the permeability. So the simulation of permeability can be performed conditioned to the trend model of porosity, which is this one here, and the permeability data. Okay. Note that the local trend, let's call it m of x, the mean, local mean. The local trend of porosity is known at every location, including the well data. So the simulation of permeability can be performed conditioned to the trend model of porosity. To estimate the local CDF of permeability at any location, for example, this one here, XU, we use simple Kriging with local means that we have learned in the introductory course of Geostatistics. And simple Kriging is this expression is no else than the trend plus the Kriging of residuals. Okay. We do not Krig the original variable, but we Krig the residuals and some at the end. The local value at that location, XU location. This is the quite simple model. These are examples. For example, this is the local trend of two views, different views, Z views of local trend of porosity, and look here another view, and the corresponding here is one realization of using this local trend of porosity. As you can see, this blue shadow is reproduced. These red, very high values of porosity also reproduced in the simulated realizations. Okay, can you see? For example, this is the local trend of porosity that we have used to simulate, and this is the mean model of the permeability realizations or simulation. As you can see, there's a quite good, large reproduction of those patterns, which means that it reproduces strong conditioning. It produces strong conditioning to the local trend image. Okay, so which means that when you assume a local trend, this must have a reliable physical meaning. Otherwise, what you are reproducing here is just a mental assumption. Okay, so now let's see a different method. It's more used, more common, and with a less strong assumption than the previous one, which is the joint simulation of two variables. Okay, they are simulated separately, not independently, separately. We have porosity, permeability, the same relationship. And the objective is to simulate Z1 and Z2 by reproducing the correlation between them. This one. So the cost simulation of joint simulation follows the sequential bias relation. So, which means that we first simulate the first variable, and the second variable is simulated conditioned to the previous simulated model Z1. Okay, let's see how it works. So this is the sequence of co-simulation. First we have to choose and simulate the main variable. Okay, just to call your attention, main means that the next variable will be conditioned to this one. Okay, so suppose that we choose Z1 here. Now we co-simulate Z2 having Z1 as an auxiliary variable and the correlation between Z2 and Z1 between them. In this case, Z1, previous simulated, is the auxiliary variable available at all grid nodes here. And Z2 is the variable to be co-simulated, available only at sample locations. Okay, so we are going, in this case, to estimate the local CDF at this location. We are going to use the collocated co-kriging estimate here. Okay, co-kriging is a linear combination of variable Z2, which is, for example, permeability, known at experimental sample location, plus the collocated value of porosity at this location here, of the target location x0. This is a simple kriging. Let me recap that to obtain this collocated co-kriging, we need to solve those two n plus 2 equations here. But what I would like to call your attention is we need to know the covariance of first variable Z1, the covariance of Z2, but also the cross covariance between Z1 and Z2. Okay. In those cases, normally we can use a shortcut, an approximation called Markov type approximation, where the cross covariance or correlograms here are calibrated by the correlation coefficient between the variables Z1 and Z2 through this expression here, which means that I obtain any cross, in this case, correlograms with the marginal correlograms and calibrated by the correlation coefficient. Okay. So the correlograms between Z1 and Z2 are entirely defined with the correlogram of marginal variable and the correlation coefficient between those two variables. Just to illustrate the influence. This is an academic exercise because normally what you do, you calculate the correlation coefficient and we proceed your co-simulation. You don't do this kind of sensitivity analysis. I'm doing just for illustration purpose. This is the main variable that are going to be used as auxiliary to simulate the secondary variable here, and we impose a correlation coefficient of 0.95, 0.8, and 0.60. Can you see the difference? When you impose 0.95, the secondary variable, the primary variable reproduce the auxiliary variable, the main patterns of quite well. Okay. Of the primary, and at the other extreme, when the correlation coefficient is not so strong, is 0.60, the patterns are not so similar. But look at the histograms; they reproduce the histograms here. The histograms are just start to be a little bit different from those ones of the first variable, and the variogram models are also quite well reproduced. Sorry.